Hey everyone, welcome back to Linear Algebra. This will be lecture 20 of the course. And in this section we're going to shift gears and move into what I would consider the fifth section of the course, the fifth of 6 sections of the course. And that's going to be a section of maybe 5 lectures on linear transformation. So this is a new kind of a new concept. It's going to build naturally on the material that we picked up in vector spaces. Also, of course, everything builds on the stuff that came before that. So let's go ahead and jump into it. So we'll call this section 5.1 linear transformations, or introduction to linear transformations if you prefer. And so let's go ahead and start with an example. Okay, let's start with an example. Let's say I have a function, and we'll call it f, and it's going to be a function from M to 3, which is the vector space of 2 by 3 matrices. So it's a function from M to 3 to M to 2, and this is the 2 by 2 matrices. Okay, and so we're going to let f be this function that maps a 2 by 3 matrix into a 2 by 2 matrix. And we have to, of course, define it. So we'll say this is the function given by, so if I take f of, let's put my matrix in here, A, B, C, D, E, F. And that's going to, once I start with this 2 by 3 matrix, A, B, C, D, E, F. And when I apply f to this matrix, what I get out is A, B, 0, 0. Okay, so f in this case is a function that maps one vector space, namely M23, into another, and that is M22. So what is the domain of f? Well, the domain of f is M23, right? And what's the codomain of f? Well, the codomain of f is M22, right? So we start in the domain, M23, we map it into this codomain, M22. And alongside that, what is the range of f? So the range of f, it's going to be a subset of M22. Okay, it's going to be a subset of M22, namely where the 2 by 2 matrix has 0, all zeros in the second row. Okay, so this is the setup, right? Now notice there are lots of elements in M23 that map to a given M22 element. So for example, we could say that the image, right, the image of the matrix 1, 2, 3, 4, 5, 6 is what? Well, basically A and B are the only thing to get mapped over, so it's 1, 2, 0, 0 under F, right? So when I apply F to this matrix, I get this guy. But there are infinitely many matrices that'll map into this guy, right? Okay. Also, I could say what? 1, 2, 10, 11, 12, 13 maps to 1, 2, 0, 0 also, right? So there's lots of things in the domain of f that map to this particular instance in the range, but notice there's only one thing that everything in the image will map to, right? So it's a function truly, right? Meaning there is literally one thing that is mapped to, okay, in each case. Okay, and this is kind of this is a nice introduction to the idea of a linear transformation. I mean, it's kind of a little more of a little bit of a recap of some of this terminology, right? But this is essentially a linear transformation, right? It's a function that we apply to vector spaces. Okay, let's formally define linear transformation. Okay, let's formally define this. So we'll let V and W be vector spaces. So we'll let V and W be vector spaces, and let's let F be a mapping from V to W. Okay, we'll call it a function. We'll let F from V to W be a function from V to W. Okay. Right, so to clarify here, for all V and V, let me put this in here, that is, and this is kind of an aside, that is for all vectors in V, right, F of V is going to denote exactly one vector in W. Okay, right, that's what it means to be a function, right? Okay, so just to make that explicit, that's kind of what the previous example sort of showed you, kind of refresh your memory on this idea of a function. And it's very important when we're talking about linear transformations that we are talking about functions. So let V and W be vector spaces, and let F be a function from V to W. Okay, then F is a linear transformation. It's a linear transformation if and only if the following two things hold. There's two properties to a linear transformation. So the first one is that the function applied to a sum of matrices is equal to the sum of the function. Okay, so the function applied to the sum is equal to the sum of the functions applied separately. Okay, and this is obviously for all V in V, for all vectors in the domain. So that's the first one. And then second, so this looks a lot like vector addition, basically, right? So vector addition works, and in fact, it allows you get the same result irregardless of whether the operation is performed before or after the function is applied. And the second one is going to naturally pertain to scalar multiplication, right? So F applied to a constant C times a vector V is going to equal C times F applied to just V. And this, of course, is for all C in R and V in the vector space. Okay? So these two properties are, on top of the function between two vector spaces is going to define a linear transformation, right? And so what do these do? These two properties basically insist that the operations of vector addition and scalar multiplication, the two key things for your vector spaces, the operations of vector addition and scalar multiplication give the same results, you get the same answer, irregardless of whether the operations are performed before or after we apply F. Okay? So you can kind of think of it as a linear transformation is a function between vector spaces that preserves the operations that really give the vector spaces their structure, right? So this, namely vector addition and scalar multiplication, those two operations are preserved whenever you're dealing with a linear transformation. Okay, all right, so that's the definition. Now let's do some examples and make sure we can see how this manifests. Okay, so let's start with an example here of, let's consider F as a function from m by n matrix to an n by m matrix, right? So you start, the domain here is an m by n matrix, the set of all m by n matrices, and the codomain here is the set of all n by m matrices. So we're going to let F be a mapping like this, given by F of a matrix A is equal to just the transpose of A. Okay. Now, so that's the function we're defining. Now let's confirm that this is a linear transformation. So let's confirm that this is a linear transformation. Okay, and so basically we got to confirm the two properties. Right, the first property is that f of a1 plus a2 is equal to f of a1 plus f of a2. We got to confirm that one to start with. Okay, so we can do this. This is really straightforward, actually. Let's let a1, a2 be matrices in M, Mn, right? M by n matrices. Then what do we do? Well, we can apply f to them. What does that mean? Well, basically, it's a1 plus a2 transpose, right? Okay, and we've seen this when we talked about the transposition of a matrix back in what I suppose like, I mean, it was early in section 1 probably, right? Section 1 where we probably talked about maybe lecture 3 or 4 where we talked about the transposition of a matrix. Well, what we said was if you have a sum of two matrices and you transpose the sum, then it's equal to a1 transpose plus a2 transpose, like this, right? So you can just separately transpose and then add them, right? We saw this early on. And so then, of course, this is just f applied to a1, and this is just f applied to a2. Okay, and so that's what we need to show. So basically, this guy here is equal to this here. That's the first property of a linear transformation. Okay, and so what about the second property then? Well, the second property we need to show is that f applied to C times a matrix A is equal to C times f applied to just A. All right, so again, let's let C be a real number, and let's let A be an m by n matrix. Okay. Then this one is extremely straightforward as well, right? So f applied to C times A, well, that's equal to C times A transpose, right? That's all that means. And we know, again, from probably the third lecture of the course, that when we transpose a scalar times a matrix, the scalar can just come out of the transposition, can't it? So it's fine to write it like this. Okay, and then we know, of course, that A transpose is just F applied to A. Okay, and so naturally we get the equality that we seek. Okay? And so because of these two properties being true, you know, we can therefore say F is a linear transformation. Right? It's a function between two vector spaces which preserves vector addition and scalar multiplication. Okay, so F is a linear transformation. Okay, let's take a look at another example. It's good to start with examples. When you define something, you should see some examples of it. It's always the right way to go about it. Let's consider the function, we'll call it g this time, and that'll be from Pn to Pn minus 1. Now remember, Pn is the vector space of polynomial functions of degree n or less, and therefore Pn minus 1 is the vector space of polynomials of degree n minus 1 or less. Okay, and so we'll say g is this mapping, and it's given by g of p is equal to p prime, right? So i.e. that we're talking about the derivative here. That is, g is the derivative. We know that if we take the derivative of a function, right, it does indeed map to a lower polynomial space, right? Let's show that g is a linear transformation. right? So let's prove the two properties. So first thing we need to show is that the sum, when we apply g to the sum, we get the same answer as if we apply g separately and then added, right? So we'll start with g of p1 plus p2. Okay, and so that just is equal to p1 plus p2, and we're going to take the derivative of that. Now, you may recall from calculus, right? Let me write it slightly differently. If I take ddt of p1t plus p2t, this is sort of the notation that we're used to from calculus. I know that I can break the sum apart, can't I? I know, for example, that that's equal to ddt of p1t plus ddt of p2t. Right, you might remember that from calculus. Well, another way to write that, simpler way to write it, is just p1 prime plus p2 prime. Right, and this is just taking the derivative separately of the two polynomials and then adding them together. So that is obviously just g of p1 plus g of p2, since g is the function, is the act of taking the derivative. When we apply g to a polynomial, we're taking the derivative. Okay, and so that's what we wanted to show, that is equal to that. Okay, and so seeing that, you can probably imagine that the second property is going to be really easy to show as well. So looking at number 2, g times g taken well, when we apply g to a polynomial times a constant, so here p is a polynomial, c is a constant, then that just means we're talking about c times p prime, like this, right? And so again, converting this to like the notation from calculus will make this really obvious, that if I asked to take the derivative of c times a function pt, then you may recall that it's appropriate to pull the constant out of the function and take the derivative of the function without it, right? So it's fine to do this. Right, so that's something we saw in calculus. And so another way to write that is c times p prime, right? And so that, of course, is just c times g applied to p. Right, so here we have the scalar multiplication property. And so g is a linear transformation, right? Certainly a function, and it is a function that preserves vector addition, scalar multiplication. All right, maybe a slightly trickier example. Let's let V be a finite dimensional vector space. Okay, so V is a finite dimensional vector space, and let's let B be an ordered basis for V. Okay, so V is a vector space, and B is a basis for V. It's not just a basis; it's an ordered basis, and that means we can use the fact that B is ordered means we can use coordinatization on it, right, on V. So basically what this is going to imply is that for every element V, right, every vector in the vector space V, there is a coordinatization under B, right? So basically what that means is you've got, for every V, you've got this guy, V coordinatized under B. Okay, right? So this is just kind of the wind up for this example. Okay, and so now we can define the function. Let's let F be the function from the vector space into Rn. Okay, and so here we're assuming that V is n dimensional. It's n dimensional, meaning that it has n basis vectors. So let f be the function from the vector space V to Rn, given by, what do you think it's going to be? Well, it's going to be the coordinatization of it, isn't it? So f of V is equal to basically the coordinatization of V under B. Now we know that this is unique. Every vector has a unique coordinatization under B, right? That's because B is a basis, therefore everything in B is linearly independent. So the linear combinations for each vector V is going to be unique with a basis. And then the fact that we ordered it makes it truly unique. Okay, so this is definitely a function. Now, is it a linear transformation? Let's see. So we'll say f is a function. Come and I'll write here, make sure you know why. Right, that's important. I kind of gave the explanation for why it's a function, but make sure that that all makes sense to you. But is it a linear transformation? Let's see. So the first thing is we got to prove the vector addition. So we'll consider f of v1 plus v2. So obviously v1 and v2 are vectors in V. And so when we apply f to that, basically we're going to coordinatize that sum. Right? So v1 plus v2 coordinatized under B. Now, we had a theorem when we talked about coordinatization, I believe it was the last lecture, where we basically said that, well, by theorem, and I'll ask you guys to double check and go back and look, by theorem we were shown that when we were talking about the properties of coordinatizations, we were able to prove at the time that if you have a vector x plus a vector y coordinatized on an ordered basis B, that's equal to this, which is exactly what we need, right? So this is a theorem from the previous section, and so we can just kind of jump right to the punchline here. We can break those apart. We know that they're equal. And then, of course, that means this is just f of v1 plus f of v2. All right, again, by theorem. All right, we talked about this in the last section. All right. And the second property, again, we discussed in the previous section as well. So if I have f of c times a vector, okay, then I know, basically when I apply f to the product, to the scalar product here, I get c times v coordinatized under B. And again, by theorem, that was equal to c times the coordinatization. Right, so this one's really obvious if you just finished talking about coordinatization, and if you can just look back and you can find that theorem in the previous lecture, this one it follows directly. All right, but this is certainly an interesting kind of function. Well, this is not a function that maybe we've thought about. And truly, like the previous example as well, thinking of the derivative as a function is a little bit different probably as well. Okay, so these are all examples of linear transformation, but notice like not every function is a linear transformation, so let's take an example of one that isn't. Let's find an example. So not every function is a linear transformation. Here's a counterexample, right? So let's let h be a function from R2 to R2, obviously two vector spaces. Okay, and let's define it as h of xy is equal to x plus 1 comma y minus 2. It's kind of a seemingly straightforward function here, right? Right, and so we know that this basically means you're going to take xy, whatever xy is, and you're just going to add 1, negative 2 to it. So it's the same thing, right? Add 1 to the x component, add negative 2 to the y component. And let's, you know, so if we were to try to prove that this is a linear transformation, we would run into trouble. It's very easy to find a counterexample. It's very easy to find a counterexample to show that while this is a function, it is not a linear transformation. Okay, and so here's a counterexample. We'll take two vectors will be here. Hold on, let me write them out. So x will equal 1, 2, and y is equal to 3, 4. Okay, now if I apply, so hxy then is equal to h applied to 1, 2, and 3, 4. Okay, and so what does that mean? Well, what it means is I'm going to take 1 plus 1, comma 2 minus 2, plus 3 plus 1, comma 4 minus 2, right? So this is the first one, adding 1 to this guy, subtracting 2 from that guy. And then the second one, adding 1 to the 3 and subtracting 2 from the 4. So you get this. Right, and so I can go through that, and I see that this is 2, 0, plus 4, 2. And so what do I get? I get 6, 2. Hold on. Oh, shoot. You know what I did? I did slightly wrong. Sorry about that. I'm kind of working it backwards here. That's okay. That's okay. So this is 6, 2. Okay. So actually here I've applied h separately. Oh, let me try this one more time. I applied h separately. First you have to add them together, right? So let me try that one more time. So this would be h of, so 1, 2 plus, I should be adding there. That's what threw me off. Okay, so this would be h of 1 plus 3 is 4, and 2 plus 4 is 6. Right, so it's like this. So I first have to add the vectors, and then I apply h. All right, and so when I apply h to this, I get 4 plus 1, and then 6 minus 2. So I get 5, comma 4. Okay, now what happens when I do it this way? Okay, and if I apply them separately, but notice that h of 1, 2 plus h of 3, 4, well, that's what we actually did here by mistake. So that is going to give me 1 plus 1, comma 2 minus 2, right? That's this one, plus 3 plus 1, that's this one, comma 4 minus 2. Okay, so what do I get? I get 2, 0 plus 4, 2. And so this is going to be 2 plus 4 is 6, and 0 plus 2 is 2. Right, so they're not equal, is the point. Okay, and I kind of butchered that example, but you can trace through that again. But the punchline is, if I add the vectors first and then I apply h, I get 5, 4. But if I apply h separately to the vectors and then add them, I get 6, 2, right? So vector addition is not preserved for this function, right? And you could similarly show that scalar multiplication doesn't work, right? You can similarly show that vector or scalar multiplication is broken for this function as well. And so, because of those reasons, this is not a linear transformation. It's still a function though, right? There's nothing wrong with this function. It's every element in R2 when applied, when you apply this function, every element in R2, you definitely get a unique element, but that mapping, that function, does not preserve the vector space properties, and so it's not a linear transformation. Okay, Very good. All right. Let's refine. We're going to do some refinement of this definition and look at some more examples. So let's let V be a vector space. Then a linear operator on V is a linear transformation. It's a linear transformation whose domain and codomain are both V. Okay, so a linear operator is a special case of a linear transformation where the vector space you're starting in is the same as the vector space you're ending in. That's called a linear operator. So there are a couple of trivial examples that we should talk about just for the terminology. So if V is a vector space and I is the mapping from V to V given by I of V equals V, then in this case, this is what we call the identity linear operator. Okay, so this is a linear transformation, and it's what's called the identity linear operator. So it's a linear transformation. You could show that. It's obvious if it's a linear transformation, it's obviously a linear operator because every vector just basically stays put. So obviously the domain and the codomain are the same, so it's a special case of a linear operator. It's called the identity. Now another one is this guy, Z from V to V. So V being a vector space given by Z of V equals the zero vector is called the zero linear operator. Okay, so that's another example of a linear operator, kind of the trivial one, right? But there are lots of linear operators that aren't trivial. So let's quickly hash out some of these really important ones. And these are, let's start with this one. This one is called a reflection. Okay, so, and we'll take an example of a reflection on R2. So if I start with a function from R2 to R2, given by f of AB equals f of a negative B. Okay, this is what's called a reflection. This reflects the vector AB across the x-axis, right? So if I have my plane and AB is up here, well, where's a negative B? Well, it's down here. Right, so it reflects across the x-axis. You could also set up a reflection across the y-axis if you like by making f of a b equal negative a comma b. Right? So you can see how this is a simple reflection. It's obviously a linear, well, maybe it isn't obvious, but it is a linear transformation, and if that's the case, it's obviously a linear operator because it maps R2 onto R2. So that is an example of a linear operator, and this is specifically the case of reflection. And so you can reflect across any axis, right? Here's R2 to R2, but you could expand this to R3, and you could flip across the XY plane, or you could flip across the XZ plane, or whatever. You could do this in Rn and flip across whatever axes you would like. So that's called a reflection. How about this guy? This next one is called a contraction or dilation depending on how you set it up. But this is going to be a function, and we'll call it g and we'll just go Rn to Rn. Okay, and it's given by g of v is equal to c times v. Now, the scalar c is going to determine whether this is a contraction or a dilation. If c is less than 1 in absolute value, then this is going to contract. If c is greater than 1 in absolute value, then it's going to dilate, meaning it's going to stretch. Right? It will either shrink or stretch, contract or dilate, respectively. Again, this is a linear operator. Another example of a linear operator is the projection. Okay, so consider h on R3 into R3. Okay, given by h of a, b, c. So you start with a vector a, b, c, and when you apply h to it, it maps to a, b, 0. Okay. So what is this happening here? This is going to project from three-dimensional space onto the xy plane. Okay. Excellent. All right, so this is a projection. And one more example. This is a little more involved. Let's talk about rotations, basically. We're going to let theta be a fixed angle. And we're going to say it's in R2, right? So think about rotation on the plane. Okay. And then we're going to say L is the function from R2 to R2 defined by, okay, so we're going to say L of a vector xy is equal to a product here, a matrix product. So this is going to be cos theta, negative sine theta, and then sine theta, cos theta. All right, that's a matrix times xy. Okay, so that's the function. Basically, the function L takes whatever xy is and multiplies it by this matrix. And so in this case, you will get what? X cos theta minus y sine theta as the first component, and then x sine theta plus y cos theta as the second component. Right? And you could spend some time thinking about this and working on, maybe doing some plotting and trying to figure this out. I mean, you really just need a couple of examples and you'll kind of see what's going on here. But basically, this is a linear operator. This rotates xy counterclockwise in this case. By the way this is set up, it's going to rotate it counterclockwise through the angle theta, whatever theta happens to be. So if theta is pi, it's going to be a 180-degree rotation counterclockwise. Right? So you can imagine if I have a vector like this, if theta is equal to pi, then when I apply L to, so if this is v, then L of v is down here, right? It's going to rotate it theta. Right, so every vector is going to be rotated, so this is obviously a linear operator from R2 to R2. Okay, is it obvious that this is a linear transformation? Maybe not. Let's actually run through this one. Why is this a linear transformation? I already said it is one, so I'll just put yes there, but let's test the properties. So let's look at L of v1 plus v2. Okay, so L, if I apply that, that basically means I have to multiply by this matrix. Right, so it'll be like this. These are vectors, so let me put that on there just to make sure. Okay. And what happens when I multiply in this fashion, a matrix times the sum of two vectors? I can distribute, right? We know that from early matrix and vector operations. So this is cos theta negative sine theta cos theta times v1 plus cos theta negative sine theta cos theta times v2. Okay, and so clearly you can see that this is applying L to v1, this is applying L to v2. So I get L of v1 plus L of v2, right? So that's the first property. The second property is really obvious, so I'll just, kind of state it. But L applied to C times V is obviously equal to C times L of V, right? Spend 2 seconds and confirm this. Pause the video and just basically do the exact same thing up here, and you'll see that, oh, clearly I can clearly pull out the C here. Okay. So this example here, this rotation example, this is really like a special case of the next example, which the next example is going to be about matrix multiplication in general. Okay, so let's let A be an m by n matrix, and we'll define F from Rn into Rm by F times the matrix, or the vector x, is equal to A times the vector x. Okay. So this is so you can clearly see that the previous example was multiplying a vector times. The linear transformation was defined as multiplying the matrix with the trig functions in it by the input vector. And so this is just a more general sense, general case, right? And so this one is going to work for exactly the same reasons as what we just showed, right? So to see that this is a linear transformation, let's look at the properties, and this will be just basically like what we talked about before, but just generally, right? So if I start with f of x plus y, where x and y are vectors in Rn, then that's just equal to A times x plus y, like so. And for the same reasons we just discussed, this is just A times x plus A times y, and so that means this is just f of x plus f of y. Right, so this right here, this is section 1 of the course, right, where we learned about basically matrix multiplication. And obviously property 2 is the same idea. F of c times a vector x is equal to A times c times vector x, which is equal to c times A of x, right? Again, this is section 1 stuff here, this equality here. And so we can see that that's c times f applied just to x. Okay. All right, very good. Okay, very good. So we've talked about what a linear transformation is. We've done a number of examples of linear transformations. We've talked about linear operators and done a bunch of examples of linear operators. Now let's talk about some additional properties of linear transformations. I mean, we already know a few properties, namely that the definition stipulates that this is equal to this, and this is equal to this. But what else is true of linear transformations? Okay, what else is true? Well, let's let V and W be vector spaces. And let L be a function from V into W. And we're going to say L is the linear transformation. Okay, so L is a linear transformation. And then we're going to let the zero vector of V be denoted like this. And we're going to denote the zero vector in W also. Right, so every vector space we know has a zero element, and that's what these are denoting. Okay, so then we got a couple properties. So the first one is that if I apply the linear transformation to the zero vector in V, then guess what I get? The zero vector in W. That's nice. I don't know if that's unexpected. I mean, when you see that, like, oh, that's nice. That means the center of the vector spaces are retained. But it's kind of obvious when you think about it for a second. But at first, it's maybe potentially a little surprising. It's also true that if I apply the linear transformation L to the negative V, then what I get is equal to negative L of V, right? So that one is kind of more obvious. It's just a scalar multiplication argument, I think. And then finally, when I apply L to a linear combination, that's gonna produce A1 L V1. It's gonna produce results that are equivalent to basically this. Okay, which this is not unexpected, right? The definition of a linear transformation says that the linear transformation preserves scalar multiplication and vector addition, and so this is not surprising. Let's prove these three. Let's prove these quickly. We'll prove 1 and 2. 3 is really, I'll leave to you because I think it's really straightforward. But 1 and 2 are actually relatively straightforward as well. So if we apply L to the zero vector in V, then that's equal to L times the scalar 0 times the zero vector in V, right? And we know this is from a previous section, right? Why? Well, we know it from a previous theorem. Basically, 0 times V is equal to 0 vector. Okay, so 0 vector is a vector. I apply 0 times that vector, and I get the 0 vector, right? So this is all totally legal. Now I know I can pull a scalar out, and I get this. Okay, and then so whatever vector this happens to be after I apply the linear transformation, when I multiply it by 0, it's definitely going to be the 0 vector in W, isn't it? Right, so the linear transformation applied to the 0V is going to give me a vector in W by virtue of the fact that it's a linear transformation. And then when I multiply it by the scalar 0, it becomes the 0 vector in W. And so this is definitely the 0 vector in W. Almost feels like a cheat, but it's not. It's not. Right, and so this is again kind of using this previous idea. So that's the first one. The second one, here we start with a linear transformation of negative V, where V is a vector, in the vector space. And so this is equal to L times negative 1 times V. right? And so we saw this in a previous theorem here. Basically, we said -1 times the vector is equal to negative the vector. Okay. And so again, kind of, you have to go back and look at the early stuff of vector spaces here. Okay. And so we can pull the scalar out. We just saw that. So -1 times L of V. And so we get negative L of V, which is what we're trying to prove. Okay, so that's fine. Good enough, right? L of V is a vector. A -1 times a vector is negative times the vector, negative vector, right? Okay, and then 3, I think I'll leave up to you. Again, it's a straightforward argument. Basically, apply the definition of a linear transformation, and then you can use induction to prove it. Okay, new theorem. And so we talked about function, so we introduced the function, and we talked about how linear transformation is a special kind of function on vector spaces. And so kind of a natural thing to come up would be the idea of composition of linear transformations. So that's what this theorem addresses. So let's let V1, V2, V3 be vector spaces. Okay. And we'll say L1 is a function from V1 to V2. It's a linear transformation. And L2 is a linear transformation from V2 to V3. Okay, so I've got these two linear transformations. Then L2 composed of L1 is a function from V1 to V3. Okay, so L2 composed of L1 is a function from V1 to V3, and we can say given by, let's write it in the other way, the other notation is sometimes more useful. L2 composed of L1 of V, okay, for all V in V1. Right? This function, this composition here, is a linear transformation as well. Right? So basically, if I have two linear transformations and I compose them, then I get a new linear transformation. Okay? So the composition of linear transformations is a linear transformation. Let's see an example here. Let's do a nice example. Let's let L1 be the rotational linear transformation. The rotational linear transformation from before, right? So, and we'll think about this in terms of R2. So L1 is from R2 to R2. Given by, what was it? It was L of xy equals the product cos theta negative sine theta cos theta, that matrix times xy. Okay, so that was the first linear transformation. We'll call that L1. Okay, we know that that's a linear transformation. We went through that exercise and saw that. L2, let's think about L2. Let L2 be the reflection linear transformation. Okay, so L2 was, again, we'll go R2 to R2, given by L2 of a vector xy was equal to, we'll say x negative y. Okay, so this is going to flip the vector across the x-axis. All right, so we've got two linear transformations here. We got a rotation and we got a reflection. Now the composition, according to the previous theorem, the composition ought to be a linear transformation as well. right? So let's talk about what that thing looks like. So what is L2 composed of L1? Well, it looks like this, doesn't it? L2 composed of L1 of a vector v, right? So that's going to be equal to L2 of the vector, let's say v is equal to xy. Okay, so we need to label this. But if I apply L1 to v, then I multiply cos theta minus sine theta, cos theta times xy, and I get x cos theta minus y sine theta, and then x sine theta plus y cos theta, right? So this is the vector that I get. xy is what I start with, and when I apply the rotation, I get this vector, right? The first component is the top section here, is this top expression. The bottom expression is what y becomes. And then when I further apply L2, which is the reflection, then this gets transformed into x cos theta minus y sine theta. Again, that component stays the same. The lower component gets flipped to a negative. Negative sine theta plus y cos theta. Right? And so this would be the composition L2 composed of L1. Right? So what does this do? Well, it basically rotates v through whatever angle theta it happens to be, and then it reflects the result across the x-axis. Okay, so this rotates v through theta, then reflects that result across the x-axis in this case. Okay, so that's a linear transformation. In fact, it's a linear operator. Right, so L2 composed of L1, it goes from R2 to R2. Right, if I start below the x-axis, I end up rotating and then flipping back across. Well, it depends on what theta is, whether I flip across the x-axis or y-axis. But if I end up above the x-axis after the rotation, then I get flipped below, right? And so everything in R2 is covered, is basically what I want to emphasize there. Okay, and so compositions of linear transformations are linear transformations, and we just really talked about two linear transformations, but that result generalizes to n linear transformations. So we could say let L1, L2, ... Ln be linear transformations. Then Ln composed of Ln minus 1, composed of ... composed of L2, composed of L1 is a linear transformation as well. Now, provided, right, that the composition makes sense, right? So sometimes you can't just willy-nilly take two linear transformations and compose them. The domains and the codomains all have to kind of align. But if they do align, then you do get a linear transformation automatically, right? So this is a linear transformation as well, and then I'll say provided that the composition makes sense, right? So obviously that's important, okay? All right, okay. So we can compose an arbitrary number of linear transformations, provided the composition makes sense, then the composition is itself a linear transformation. Very nice. That's the kind of behavior you like to see. Okay, let's talk through one more theorem, and this will just kind of set up, this is just kind of a nice, kind of a beautiful structure here. This shows off, highlights the beauty and the structure of these vector spaces and linear transformations on vector spaces. So it's a theorem specifically about subspaces when dealing with linear transformations, how subspaces act. Okay, so theorem. Let's let L be a linear transformation from V to W. Okay, so I've got a linear transformation L from V to W. Two things. So the first thing, if V prime is a subspace of V, right, so V prime is a subspace of V, then the linear transformation applied to V prime, right? So if I take the subspace of V and I apply the linear transformation to it, then what is that? Well, let's define that. That's going to be all of the vectors L of V such that V is in V prime, right? So I start with V prime and I apply the linear transformation to it, and I get a whole bunch of vectors, all of which have as their domain the subspace V prime. But L of V, this is called the image of V prime. The image of V prime, and specifically in W. Okay. So if V prime is a subspace of V, then the image of V prime in W is a subspace of W. Okay. It's a subspace of W. Okay. All right. Okay. And so I guess in particular what you'd say is that the range of L is a subspace of W. Right? So in particular, the range of L is a subspace of W. Okay. All right, so that's the first one, right? So basically if I run the linear transformation on a subspace of V, then the image of that is a subspace in W. Right, so nice, right? Meaning like you have closure, right? Obviously I have closure in V prime, but I also have closure in L of V prime. Excellent, right? So this is a closed subspace of W. This is a closed subspace of V, and its image is a closed subspace in W. Now the other direction works as well, right? So the other direction kind of can be worded like this. So if W prime is a subspace of W, if W prime is a subspace of W, then L inverse of W prime, right? So the linear transformation going the other direction, and we would say that's equal to all of the vectors such that L of V is a vector in W prime. Okay, so these are in V. These are obviously in W prime, right? Because I'm reversing the linear transformation. So we would call this, what would we call this? This is the pre-image of W prime. The pre-image of W prime in V. So this is a subspace of V. Okay. Right? So if I start in W prime, a subspace of W, remember W is the codomain here. Right? So if I take all of the elements of the subspace W prime in the codomain, and I apply the inverse linear transformation, then I get what you would consider to be the pre-image of W prime in V. And this is also a subspace. Okay, so it kind of looks like this, right? Here's kind of the way to think about it. I've got my two vector spaces. Over here I've got V, and here I've got W. Now inside of V, I have some subspace V prime. And inside of W, I've got some other subspace called W prime. Now, L, if I map all of V prime, it's going to land in W prime. That's what L does. L applied to V prime gets me W prime. And, of course, the reverse is true as well. L inverse maps everything back to V prime. L inverse of W prime maps everything back to V prime. Right, so basically the idea here is that the subspaces of V correspond to the subspaces of W. Okay. Right, and so that's remarkable. Right? It shows a lot of a tremendous amount of structure to subspaces and also to the linear transformations that operate between them. Okay. All right. I think that's a great place to stop. And next time we will continue on with our discussion of linear transformations. We'll look at a very important class of linear transformations, and these are linear transformations that are obtained via the product of a vector with a matrix. And so we'll talk about the matrix of a linear transformation. So we'll leave it there, and we will talk to you all next time. Take care.